Okay. So on Tuesday's lecture, we were looking at we'd moved on from that smokers problem, and we were looking at other simple flows that we might formulate by just adding a couple of our building block flows together. Okay. And the case that we were looking at was this this example where you have a source issuing from the origin of a 2D flow, and you have a uniform flow superimposed that's coming from right to left. Okay, so remember the stream function is just that linear supposition of those two building block flows. All right, so the stream function psi is just equal to the stream function for that uniform flow coming from right to left. So in this case, it's that flow's heading in the negative x direction, so it's minus u infinity y, plus that stream function due to the source, which is just q on 2 pi theta, okay? And we know that we can write theta as arctan y on x in this Cartesian coordinate system. And we saw that basically this ratio of that velocity of the uniform flow to the strength of the source was key to the flow topology that we got in this case, all right? So just like for that smokers problem where that ratio of the strength of the source to the sink was critical in terms of determining that final form of that flow topology, you get some sense that that ratio of the... So in that smokers problem, it was a kind of ratio of the strength between those two building block flows that we were using. And again, in this case, I guess it really comes down to, in some sense, it comes down to that ratio between the strength of the two building block flows. That strength in this case being the magnitude of that uniform flow u infinity, and the strength of that source, which I'm calling qs, all right? And if that uniform flow was strong enough, we saw that that plume was just kind of swept, that the source was just swept downstream in the form of this plume, okay? And I think even by just looking at that streamline pattern, you should get a sense that there's a separation or a demarcation in that flow field between the flow that's issuing from the source and the flow that's coming from upstream from that uniform flow. And that demarcation effectively is this line, this streamline that passes through the stagnation point, this separatrix that we've been considering so far in this course. All right, so sketching. You've been attending tutorials now. Have you sketched any potential flow solutions in the tutorials, or you've just been kind of being tortured with algebra? Yeah, okay, that's good. So at least they're doing something displeasurable to you. All right, so once you get done being tortured with algebra in tutorials, you should make sure that you get plenty of practice of sketching these potential flows. And I have to say that, you know, like one end goal of this course would be that I could give you some kind of target flow, say a superposition of certain building block flows, and you'd be able to analyze that algebraically and kind of sketch on a piece of paper what that flow would look like. And I tried to go through this in Tuesday's lecture, but we'll just quickly do it on overhead, so there's a record of it recorded on Lectopia, all right? So you should be able to sketch a flow. So in this case, we've got a source and a uniform flow. The first step to being able to sketch that flow is that you've got to be able to determine where the stagnation points are. So that means you've got to be able to write out expressions for the two velocity components from a given stream function. But you all know how to do that, right? You just differentiate that stream function with respect to y and respect to x, okay? And then the stagnation points are just positions where u and v are both equal to 0, so where that flow really does stagnate or come to a rest. So we worked out where that stagnation point is, and I'm telling you that stagnation points are always saddle nodes, okay? So there's always two streamlines coming in and two streamlines coming out. And I don't know which way round that is. There could be two coming out this way and two coming in this way. But it's always going to be a saddle node topology, which is going to help us sketch this flow. And then also on Tuesday, we wanted to sketch the separatrix, okay? Very easy to do if you've got a computer or MATLAB lying around, but in the absence of that, we need to help ourselves with sketching that separatrix. So what we did, what did we do? So we know that the separatrix is a streamline, so it's a line of constant stream function. We worked out what that constant was at that stagnation point, and it was happily equal to 0. Okay, so that separatrix is just a streamline or a line of constant stream function where the stream function is everywhere equals to 0 along that line. So by just setting that stream function equation equal to 0, we were able to, and then setting y equals to 0 in that equation, I was able to find those points where the separatrix crosses the y-axis, and by setting x equals to minus infinity, I could find where that separatrix was asymptoting to in the limit, okay? So then we can sketch the separatrix, and I know what direction the flow is going along that separatrix. I know that from that saddle node condition at the stagnation point. That's quite critical, okay? Remembering that stagnation point is a saddle node is kind of critical. And then, basically, you consider the flow close to the origin, remember it, and you know that close to the origin, the flow's got to resemble the source. Everything's got to be flying out radially from that point source. And you should remember these rules. The streamlines can never cross, and those streamlines where they come close together, or adjacent streamlines, must be moving in the same direction. So when they come together, they've got to be moving in the same direction. So then I can sketch what's going on with the source by considering the origin, and I know that in the far field upstream of that source, the flow must just resemble the uniform flow. And again, I remember that rule that streamlines can't cross, and when they come close to that separatrix, they must be flowing in the same direction. So actually, there's only one way that you can sketch this flow if you follow those rules, okay? I know that it's kind of, maybe it's not very believable because we'd already seen the flow before we sketched it. But you should try it in your tutorials. Once you've found the stagnation points, usually you can have a fairly good stab at sketching that flow. And there's only really one way that you can sketch it, as long as you remember those simple rules and you locate those stagnation points correctly. Okay, so finally on Tuesday, what we did was, again, we said that since the flow is purely tangential to a streamline, any streamline in our flow field can be represented with a solid body, okay? So what we did was just replace that curved separatrix and said it was a solid body, say the nose cone of a vehicle. And I guess I could have done that with any streamline. The reason that we did it with the separatrix is because it's, well, I guess because it's a classic solution, but more immediately because we had an equation for that line of separatrix that we derived on Tuesday. We knew it was this, you know, x was related to y via this cotan expression that we're going to use later on in today's lecture. And that body is called a half-ranking body, so no surprises for guessing what the full-ranking body is going to look like. That's going to be the pleasant surprise at the end of today's lecture. So, did we talk about pressure on Tuesday? We just started. Oh, yeah. Right. So you horrified me because you didn't remember that you used Bernoulli's equation for relating pressure to velocity. But you did get there in the end, okay? So what we wanted, we know the velocity field, we know the flow field around this geometry, this half-ranking body, which we could use to model a nose cone. And what we'd want to know is the pressure distribution really acting on the surface of that body, because that's going to tell us the wind loading on that body. It's going to tell us, for example, how much thrust we need in order to keep that body moving along, okay? So the question is, can we just apply Bernoulli's equation? And the answer to that is, not to give too much away, but yes, we can, all right? But Bernoulli's equation has this very nice condition, or this very nice I guess a reduced limitation for us for these 2D inviscid incompressible flows that we're dealing with. And I'll just try and explain that quickly today. So do you remember the caveats for Bernoulli's equation? You used it in your introductory fluids course, right? You probably used it as well when you were high school kids. Do you remember, did anyone give you a list of, you know, thou shalt not use Bernoulli's equation when this isn't true kind of things? Do you remember those? There's quite a number of limitations for Bernoulli's equation. Any of them? No. All right. So this is, that's all right. It's not, you're not unusual. Even in textbooks, people get it wrong quite a lot. So Bernoulli's equation is one of the most misused equations, I would say, in fluid mechanics because it's so, you know, attractively simple to use. But it does come with all these limitations that you should remember. That's why we derive it with you in introductory fluids, you know, so that we're not just trying to torture you, we're trying to make you remember all the assumptions you had to make to come up with that set of equations. So there's a lot of them, and I probably can't remember them all, but it's only valid for, the big ones are, it's only valid for steady flow when there's no additional energy input into that flow, so no heating or work extraction from that flow. And the really big one that I would have hoped you would remember is that you can only apply it along a streamline. You do remember that? You should remember that, okay? So anyway, let's just go through the derivation let's just go through the derivation for the purposes of this course, okay? So, and the derivation is very simple. We just start from the conservation of momentum equations, all right? And there's always a sneaky trick, I guess. This derivation is given on page 15 of your lecture notes. So every derivation starts with a sneaky trick, just like when we derived Helmholtz's equation. In this case, what we do is we multiply that x momentum equation, which is the top one here, by dx, and we multiply the y momentum equation by dy, okay? Do you remember the sneaky trick for the deriving Helmholtz's equation from momentum? Probably not, I guess, if you didn't remember Bernoulli's was only applied along a streamline. In that case, what we did was we differentiated the x momentum equation with respect to y, and we differentiated the y momentum equation with respect to x. There's always a sneaky trick with derivations, and I'd say that if you remember the sneaky trick, the whole derivation's easy. If you don't remember it, you're going to be staring at the page for half an hour as the clock ticks down, okay? So this has a nice property. When I do this, those, for example, if you look at those pressure terms on the right-hand side of those equations, they're going to combine in a very pleasing manner later on. So you should be able to work it out, actually, from what we have to do. Okay, so I multiplied the top equation by dx and the bottom equation by dy. And then I also assume that we've got steady flow, just like you did with your previous Bernoulli's equation. So there's nothing unsteady with that half-ranking body that we've been looking at, right? Nothing's a function of time. I'm not changing the flow or the location of the source as a function of time, so it's purely steady in time. So I can get rid of those terms that are differentiated with respect to time, which simplifies things a little bit. And then all I'm going to do is add equations 1 and equations 2 together. And I guess there you see this kind of rationale of not multiplying the top equation by the x momentum equation by dx and the y momentum equation by dy, right? I don't know whether you can see my pointer, but, so you see when I add them together, I get this kind of pleasing combination of those pressure terms, all right? If pressure is only a function of x and y, then what can you tell me that dp dx dx plus dp dy dy is equal to? I think you're saying it. I'm going to give you the benefit of the doubt because I'm always the optimist, all right? That term, for a steady flow, that term is really just reduces down to the total change in pressure, dp, okay? So we get this kind of pleasing combination of terms, at least on the right-hand side of that equation. So now the trick here is irrotational flow, right? We know that for this course, all of our building block flows are purely irrotational, and we've proven that when we add those building block flows together, the resulting superposition of those building block flows is also irrotational. And you'll see that something really cool happens. It's probably not cool, I shouldn't say that, it makes me look desperately uncool. Something pleasing happens with the algebra when we assume that the flow is irrotational, okay? So irrotational flow is that the vorticity is equal to 0, or that Laplacian of the stream function is equal to 0. However we write it, amounts to the same thing. Do you remember the equation for vorticity, or the equality that I'd have if vorticity is equal to 0? Do you remember the two velocity gradients that were involved in vorticity? It was du dy, and dv dx, right? So actually vorticity equals 0 implies that du dy must equal to dv dx, right? Because vorticity just equals, vorticity is just equal to dv dx minus du dy, okay? So if we've got 0 vorticity, I know that that condition is met. And then you've got this pleasing kind of substitution that you can make, so that dv dx term in that bracketed term that's multiplied by u just becomes du dy, and likewise that du dy term in that bracketed term that's multiplied by v just becomes dv dx, all right? And then we end up with this expression at the bottom here, and now we've got this very kind of pleasing outcome where all those bracketed terms reduce to just a total change in either u, v, or p, all right? So that first term, du dx dx plus du dy dy is just that total change in u, so it just becomes du. This other term is just dv, and this other term is just dp. So basically what we have is a form of Bernoulli's, almost a form of Bernoulli's equation, but the only thing that we've really assumed here, in addition to 2D and viscid incompressible flow, incompressibility, that was one of the other assumptions of Bernoulli's equation when you derived it previously. So the only assumption that we had here was irrotational flow. We still haven't assumed anything about streamlines whatsoever. So from that equation now, what I can do is just integrate that expression between position 1 and position 2, right? So I integrate u to u between position 1 and 2, v to v between position 1 and 2, and dp on rho between position 1 and 2, all right? And it drops out, obviously, very easily to Bernoulli's equation. The integral of u du is going to be u squared on 2, okay? So that term, integrating it between position 1 and 2 is just going to become u2 squared on 2 minus u1 squared on 2, and likewise that integral of v dv is just going to become v2 squared on 2 minus v1 squared on 2, and that integral of dp on rho is just going to become p2 minus p1 on rho. And if I gather all those terms that are in position 2 on one side of the equality, and all those terms that are evaluated in position 1 on the other side of that equality, you just get Bernoulli's equation, all right? I mean, I guess in Bernoulli's equation, you're used to dealing with the velocity vector, capital V squared, which is lowercase u squared plus lowercase v squared. But essentially, that's just Bernoulli's equation. But with this, this kind of reduced restriction, okay, because I didn't, to arrive at that equation previously, you had to integrate along a streamline, all right, to be able to get Bernoulli's equation. And that's why Bernoulli's equation for a rotational flow is only applicable along a streamline. But now, by assuming that irrotational condition, I was able to integrate it between any two positions in space. There's no limitation on where position 1 and position 2 are in space. So So I just get that basically a half rho velocity squared plus p is equal to a constant anywhere within my flow field. Okay. So does that kind of make sense? So if you've got irrotational flow, I mean, the end point of that derivation, if you remember nothing else, it's telling us that if we have irrotational flow, Bernoulli's equation is applicable between any 2 points in space, rather than that limitation that we're used to, that it's only applicable along a streamline. And actually, that derivation we just did is proof of that. We don't need to make any assumption that there's flow along a streamline. So just to give you a heads up, where I made that irrotational assumption, you could have also just, if you'd have made an assumption there that we were on a streamline, there would have been another relationship. There would have been another relationship between those partial differentials of u and x, which again would have allowed us to derive Bernoulli's equation, but then with the assumption that we were moving along a streamline. Okay. So please shout out if any of this is less clear than usual. Okay. So now what we can do is go back to that half-ranking body, and we've got this very, very useful equation now that's applicable. We've got a form of Bernoulli's equation that's applicable between any 2 points in space. So I can consider a point far upstream of that half-ranking body, and generally, you know, when you apply Bernoulli's equation, you try to apply it from a point where you know something about the flow. So in this case, we'd go far upstream of that body, where we'd presume that we knew what u infinity and p infinity were. Okay, so u infinity would just be the speed that you know, if this was a nose cone, u infinity would just be the speed that vehicle was moving at, and p infinity would just be the ambient pressure. And we can apply Bernoulli's equation along any kind of arbitrary line. Really, we can just apply it between any two arbitrary points in space, and we can write out a relationship between p infinity and u infinity, and p, u, and v at some other point in space. And typically, as engineers, we don't really, we're not too worried about how the pressure is varying in that open flow. We're more concerned with how the pressure, we're more concerned with what the pressure is at the surface of the solid body that we're considering, because it's that pressure at the surface which dictates the forces acting on that vehicle. So in this sketch, I'm considering a point on the surface of that half-ranking model. So I can rearrange then Bernoulli's equation to get an expression for p minus p infinity, which is the difference between the pressure on the surface of my vehicle and ambient pressure p infinity, right? And it's just a function of those three velocities, that oncoming free stream velocity u infinity and those velocity components at the surface of that half-ranking body. So do you remember, have you come across the pressure coefficient in previous courses? No. A very resolute no. You've come across the lift and drag coefficient in previous courses, and you've definitely come across a drag coefficient. So they're ratios of some force to an inertial force, okay? The pressure coefficient is very similar to a lift or drag or skin friction coefficient. It's a ratio of a pressure force to an inertial force, okay? So it's defined as p minus p infinity, which is really the pressure force that's going to be acting there's some area terms that have cancelled out here, divided by a half rho u infinity squared, which is the inertial term or the inertial force. So if you haven't come across it, it should at least look somewhat familiar from seeing lift or drag coefficients in other courses. Yes? No? 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 Yes? I've got a kind of equal mix of responses. So I guess if you haven't come across it, you need to know it, all right? You need to be able to define the pressure coefficient. And you also, I should say, need to be able to define lift and drag coefficients. But I think you're going to get plenty of practice of that when you attempt to write a report on the aerofoil laboratory that you're doing. Okay, so what I can do is substitute the P minus P infinity that I get from Bernoulli's equation into that expression for the pressure coefficient. And you can see that those U infinity squares are just going to cancel out quite nicely. And I'm just going to get that Cp is equal to 1 minus U squared plus V squared divided by U infinity squared. So I get quite a nice expression for the pressure coefficient within this flow field. Okay, so that equation will give me the pressure coefficient anywhere for any x or y coordinates, all right? But if I know the x and y coordinates of the solid body that I'm interested in, I can plug those x and y coordinates into the equations that I have for the u and v velocity components and get the velocity components on the surface of the solid body that I'm interested in, and then I can shovel those into that equation for the pressure coefficient, and I can get the pressure distribution around the body that I'm interested in. Does that make sense? Can you see why that equation would allow us to calculate the pressure distribution now around that half-ranking body? So we could do it numerically, all right? If you did it with MATLAB, you don't really have to solve anything algebraically. We can just substitute our known expressions for u and v into that, or just evaluate them at given positions, and we'll be able to calculate that pressure coefficient. I guess in this case, we can also do it algebraically, right? We showed on Tuesday's lecture, we wrote out expressions for the horizontal and vertical components of velocity by differentiating the stream function for this source plus a uniform flow. So we had these equations for u and v, and I can just kind of, I can put those equations for u and v into that equation for the pressure coefficient, and I guess, yeah, this is one of those instances where you've got to be persistent, because usually when stuff starts looking like that, you just give up because it's getting too ugly. But in actual fact, if you multiply out that squared bracket, that first squared bracket on the top of this expression, there's some pleasing simplification or cancellation that can occur. So when I multiply out that bracket, I'm going to have to rely on the pointer. When you multiply out that bracket, you can see that this term here combines quite nicely with this term here. And you can see that both of these terms involve u infinity. So I can get rid of that u infinity on the bottom of this expression. And it simplifies down to something that's not too terrible, okay? Obviously, that 1 minus 1 is going to cancel out. And you can also see that we've got an x squared plus y squared on the top and bottom of that last term. And that pressure coefficient reduces to something that's... This is the pressure coefficient now for this half-ranking flow solution, all right? That pressure coefficient reduces to something that's not too terrible, all right? And if you look in your... Are any of you using the PDF notes that are on LMS? You're going through that. So if you look in exercise 5.2 of those notes, you're asked to compute the pressure coefficient for a half-ranking body. And you were told to assume that Q on 2 pi u infinity was just equal to 1, okay? So that's effectively just giving you that ratio of u infinity on Q. And you can see that when you make that assumption, you get this very nice further simplification, because these terms here are just constants. So this first term here just becomes 2, and this term here just becomes 1, and that pressure coefficient simplifies down to this. You can see that it's got this actually very nice form, or very simple form, for this half-Rankine flow. All right, so at the moment, that's the pressure coefficient for any xy coordinate within that flow field. If I wanted to calculate the pressure coefficient purely on the surface of that half-Rankine body, what would I do? What would the next step be? So this is the pressure anywhere in that flow field, even in that open flow. If I want it on the surface of that separatrix, on the surface of that half-Rankine body, what would be the next step from that pressure coefficient equation? Sorry? I think someone said it. Yeah. So it's just what we'd use is that equation that we derived for the separatrix, all right? So it wasn't a trick question. We derived in Tuesday's lesson this expression for that curved separatrix, which just related x to this cotan of y. It's just water, but I wish it was vodka or tequila sometimes, I have to say. And I think I'd get away with it. So x is equal to y multiplied by this cotan term, which is also a function of y. And we've been told in exercise 5.2 that q on 2 pi u infinity is 1. So x is actually just equal to y cotan of y. And we can then just substitute y cotan y for x in that expression for Cp. And that's as far as we're going to get, right, analytically. But this is the equation now for the pressure distribution around that half-Rankine body. So just to kind of put all of that together, we've got this half-Rankine body, and we know we've got an equation for the form of that curve of that half-Rankine body, which was given to us by x equals y cotan y for that particular relationship between q and u infinity. And now we've got this expression for the pressure coefficient as a function of x, or as a function of, actually as a function of y, but we can also write it as a function of x, all right? That expression that we just derived. And just to remind you, that equation just comes from that simple, all the way back to that simple definition of the pressure coefficient. So I guess this flow we can solve algebraically. There'll be other flows that we come across later on in this course where we probably need to seek a numerical solution to find that pressure distribution around the body. But you can imagine that you know, if you had MATLAB, a few lines of MATLAB code, you could have avoided all of that algebra, right? By just directly, you'd have known the xy coordinates for that separatrix, or you could have found the xy coordinates for that separatrix using one of these Euler or RK4 codes that you're currently writing. Then you could have evaluated u and v at all of those coordinates, and then just pushed those numerical values for u and v into that equation for the pressure coefficient, and you could have immediately just plotted that blue curve without all of that agonizing algebra. So the distribution of pressure coefficient around that body looks like this blue line that I've sketched over that half-Rankine body. All right. So where the arrows are pushing, where the blue arrows are pushing into the body, there's positive pressure, or I shouldn't say positive pressure. Where the blue arrows are pushing into the body, the pressure is higher than ambient pressure, or higher than P infinity. Where the arrows are pointing outwards from the body, the pressure's lower than P infinity, so there's going to be a kind of, the flow is going to be exerting a suction on those surfaces due to that low pressure, okay? And if I include color contours here of the magnitude of velocity, you kind of get a sense of what's going on. So you know how to read one of these p-color, these pseudo-color plots, right? So the blue color indicates low velocity, and the red color indicates high velocity. And you can see that right on the nose of that half-Rankine body, we've got this low velocity. Actually, we've got zero velocity right on the nose because we know that there's a stagnation point there, all right? So low velocity means that we're going to have elevated pressure. So we're going to have a pressure that's higher than P infinity. And in fact, when that flow stagnates, we know that we're going to have a pressure coefficient that's equal to exactly equal to 1. Okay, where's my pointer? Equal to 1. All right. So, and then as we move around that half-Rankine body, that flow obviously accelerates, which doesn't show up very well here, but there's a darker red here where that flow accelerates around this body. And then you know that where you've got high velocity, you're going to get reductions in pressure. So in that case, that pressure drops below ambient pressure, and you've got this kind of suction force effectively acting on that surface. I don't think suction force is probably a very good way of describing that, but it's all I can think of for the time being. So the pressure, can you see that pressure distribution on the upper and lower surface of that half-Rankine body is symmetrical? I mean, it doesn't really come as any surprise because the flow field's symmetrical. So, I mean, in a net sense, there's going to be no force acting on that body in the wall normal direction, right? Because the pressure forces on the upper and the lower surface are just going to cancel out. An aerofoil is an obvious example where that doesn't happen. So those pressure forces are important, all right? I've tried to explain how they're important for us as engineers, but they're obviously important for this aerofoil problem because it's a geometry that's designed to generate lift, and that means it's designed to have a lower pressure on the upper surface than the lower surface in order to satisfy that condition. So for a body moving through a fluid such as that aerofoil, you can have body forces due to two things, all right? You can have normal stresses acting on that solid body due to pressure forces, and you know that, you remember that pressure forces always act normal to the surface, right? And that pressure is just equal, the force is just equal to the pressure multiplied by the area. You remember that from your earlier, from hydrostatics even, you remember that, right? All the way back at the start of your first fluids course. So we can have normal forces acting on that solid body due to pressure, and we could also have shear stress acting on that solid body due to skin friction, okay? And those forces are going to act in the direction shown as in these arrows. So they're going to try and retard the motion of that aerofoil through that flow. So in this course, we've ignored all of those viscous terms from the governing equations, which means that we have slip at... These shear stresses come about because of that no-slip condition at the wall, which gives rise to strong velocity gradients close to the surface, which gives rise to this wall shear stress. In this course, we've ignored viscosity, so we have slip at the wall, so we're not including those shear stresses into this problem. And for certain flows that we look at, that's not really a problem. So, for example, on an aerofoil, the vast majority of the forces are coming due to those normal stresses due to those pressure forces. And the shear stresses are very small. They make a tiny contribution, almost no contribution to the lift, and really a tiny contribution to the drag coefficient on that aerofoil. Okay, so that aerofoil will have some resultant force. If we consider all of those pressure forces acting around that aerofoil, it's going to have a resultant force that acts in some direction, as shown by this arrow F, all right? And typically, we decompose that resultant pressure force into two components. We decompose it into a lift, which is a vertically acting component of force, and we decompose it into drag, which is a component that acts horizontally, okay? I should say, actually, we usually define those components relative to the oncoming flow. So I'm saying vertical and horizontal in this case because that oncoming flow to this aerofoil is also horizontal. But you're familiar, this isn't entirely new to you, right? You know that lift and drag are just the decomposed forces acting on a body in a fluid flow. You should know that, okay? So if you consider a pressure, let's just have a look at that a little bit closer. If I consider some element of that aerofoil, and I'm considering this tiny element at the front of the aerofoil, we can kind of write out simple expressions for that lift and drag component, all right? So I'm going to consider this element that's got a length, it's got an elemental area dA, and I'm going to consider that there's a pressure acting normal to that element as shown on this diagram. And that pressure is going to give rise to this elemental force that acts on dA that's just going to be, that I'm going to call dFP, which is a pressure force. And obviously dFP is just equal to PdA, okay? It's just equal to pressure multiplied by area. So, and then I could decompose that elemental force into a lift and a drag component. So I could write that the component of lift acting on this element, which I'm calling dLP, lift due to pressure, is just going to be equal to minus dFP, which is minus PdA multiplied by sine theta, okay? Where theta is just defined as the angle of that surface normal, so the angle that pressure force makes with the horizontal. And likewise, I could write out an expression for that component of drag, which just equals that pressure force dFP PdA multiplied by cos theta. I'm not doing anything surprising here. I'm just decomposing that pressure force into a vertical and horizontal component. I guess the point that I'm trying to make to give you some kind of indication of what you're doing in that flow over an aerofoil laboratory is that if I now took those expressions for those elemental components of lift and drag and integrated those all the way around that aerofoil, I'd get the total integrated lift or drag that was acting on that aerofoil, and that's just a function of that pressure distribution around the aerofoil. Does that make sense? So this is the component of lift and drag on some tiny element of that aerofoil, but you know that when you do your aerofoil laboratory, you're measuring the pressure distribution. Has anyone done the aerofoil laboratory? No one is here. So I'm literally just like shoveling money down the drain. Or the people who've done the aerofoil lab have now given up coming to lectures, or it's just coincidence, all right? So in that aerofoil lab, you're going to measure the pressure distribution around the aerofoil, and then you're going to use that pressure distribution to calculate the total lift and drag acting on that aerofoil using this type of analysis, all right? So anyway, just to move on and consider the meaning of pressure for this half-ranking body, let's just analyze this. Let's just think about this half-ranking body in a little bit more depth. So at the moment, I said that I could replace any streamline in that flow field with a solid boundary, and I replaced that curved separatrix with this half-ranking body shape. But I could also replace that horizontal streamline, that horizontal separatrix, with a solid boundary if I so desired. And then that simple source plus a uniform flow is now modeling the flow over a bump on a horizontal surface. Does that make sense? So, and I know it's not perfect, okay, but you could, that could serve as an approximate model for the flow over the, say, the front of a car, or the flow, the example that I'm going to consider is the flow over a cliff, okay? So if I was a better lecturer, I would have spent ages on Google Images trying to find a cliff that looked like half of a half-ranking body, but I'm obviously not that good, okay? But, this was as good as as far as I was prepared to go, right? So you could consider that half of that half-ranking body to be modeling the potential flow over a cliff. And I know it's kind of a a simplistic representation, but it kind of tells us some interesting things about the flow. Do any of you hang glide or paraglide? No? Quite rightly so. It's a dangerous pastime, all right? But if you look at hang gliders or paraglider pilots, they like to sit in kind of certain positions relative to hills and cliffs, and you can kind of understand that from that simple potential flow solution. So this thing is a hang glider is an unpowered vehicle, okay? So it's gliding, and that every glider has a glide slope, all right, which is basically the ratio between the lift to the drag of that vehicle, effectively. Does that make sense? So, you know, if I released a hang glider from 1 kilometer up, it would glide, you know, maybe 10 kilometers before it hit the ground, hopefully quite gently. Okay, so everything has a glide slope, all right? You have a glide slope. It's just, you know, quite an aggressive glide slope, and you're not going to hit the ground so gently, okay? So that hang glider has a glide slope. So basically, it's coming down all the time, okay? But and the only way... So actually, hang gliding is a kind of a sport. Other than trying to avoid almost certain death, you're almost trying to... They're also trying to go for endurance, okay? They're trying to stay airborne for as long as they can. So, and in order to stay airborne or gain altitude, they need to find flow that's moving upwards at a rate that counteracts their glide slope, okay? So they need an upwards vector of velocity that exceeds their glide slope. So when they're sitting in front of cliffs and hills, they're basically trying to find regions where that flow is moving upwards, and they can counteract that glide slope. So I know that it's a crude approximation of a cliff, but I guess the whole point of potential flow is it's a crude approximation. But in some situations, you can have a quick look-see at a flow situation and try and figure out what's going on, okay? So another nice thing with that half-ranking body that we could do is I could... If I'm saying that half of that half-ranking body is the front of a car, I could try to simulate the gap between the car and the road, okay? So what I could do is I could move that source upwards on the y-axis, and then I'd have to introduce an image flow feature. I'd have to introduce a source also below the floor, okay? But if I do that, I can start to create flow between the front of the vehicle and the ground, okay? And I know there's still no wheels and there's lots of faults with this, but, you know, it can still teach us about what's going on. So now we've got a source located here, and I've got an image source located below the surface of the road. Does that make sense what I'm doing now? So now the flow is composed of two sources plus a uniform flow, okay? And you know, and I can change the distance of that vehicle from the road, okay? And incidentally, if we got rid of the floor now, this would also be a pretty good way of modeling a double body problem. So it would be quite a nice way of modeling a subsonic inlet to a gas turbine engine, the type of inlet that you see on a commercial. It's actually called a Bernoulli inlet, the type of inlet that you see on a subsonic commercial aircraft. But anyway, back to the car with a gap between it. So now what you can see is that I've broken the symmetry on that solid body, right? So can you see that the pressure distribution is asymmetrical now between the top and the bottom of that vehicle? Slightly asymmetrical, okay? So if I move it closer and closer to the ground, you see that that flow that occurs between the vehicle and the floor accelerates, and that pressure there becomes very low. So what do you think is going to happen now to that body because of that lower pressure on the underside? It's got a downforce, right? It's being sucked downwards. So this is something that F1 cars will frequently use. They'll try and maintain a very narrow gap between the vehicle and the road, and that generates a large portion of the downforce that vehicle needs to corner, okay? So on the other hand, if you're kind of, you know, some Fitzroy hipster driving around in your Range Rover, okay, you've got this huge distance between the vehicle and the ground and you're generating almost no downforce. So if they tried to corner very quickly, the car would flip over, okay? But that wouldn't happen because they'd spill their lattes or drop their $8 donuts before that happened, all right? So that, again, right, this very simple flow and very simple modelling kind of starts to give us some engineering insight into what's going on with certain flows, all right? So, yeah, we'll carry on Friday, I guess, tomorrow. Yes.
So does it have to be all typed out, or can it be handled in like some way?
You know, if you could I would say that for all the figures that you are generate, those should be mapped out, and then you have things in your code. So I mean, there's not much to write other than a bit of algebra. It's up to you, really. I mean, you should get practice at some point with being able to typeset algebra in some nice way. But if you're already, honestly, you're not going to use any marks.
Okay.
I think what some students do is type bits and then just scan them and go with it.
Okay. Thank you.
Hey,
I had the tutorials and I walked in there thinking, I'm really understanding what's going on. Conceptually, I'm up to date. And everything I went through, I get it, I know what's happening. Physically, I can visualize all the flows and visualize. But in the tutorial, I mean, the tutor just vomited algebra at the board, and I could not follow it. And I think it's more just the way they're doing. Like, if I stare at it long enough, I'll be like, right, yeah, I get that differentiation. I can do the maths. It takes me a bit of time. Why are we doing it? What is that doing and why are we doing it? There was none of the why behind it, so I just got completely lost.
What do you think is a good resource for people?
well, I think it's probably the
Textbook, or there's questions in the
I think you've got to, I mean, it doesn't sound like the tutors do a particularly good job, I have to say, from what you've said is true. So,
obviously, tutors.
How are you doing?
yeah, good. So we'll get out of your way. Can we talk outside so we can let this other lecture get on?
Take your folder on?
Yes.
Thanks a lot.
It's not yours, but...
And I think everything else is here.
Thanks.